Hello my friends and welcome to part 2 of this implementation training the AI. We have just built the brain of the AI in part 1, building the AI with the architecture of the neural network composed of 2 fully connected layers between the input layer and the output layer. And now we're gonna train this brain to land properly on the moon. And our first step here will be to set up the environment. That will be a very simple step. So here we go. Let's do this one in this tutorial. So we're gonna create a new code cell. And the first thing we're gonna do, of course, in order to set up the environment, first we have to import Qlearning, which contains all the environments that I introduced to you in the first tutorial of this module. So here we go. We're gonna import Qlearning, and we can give it a shortcut like Gym. All right. Then, now that we have Qlearning, well, we can import the environment in which our AI will be trained, meaning the Lunar Lander V2 environment, exactly this one here. So let's go back to our implementation and let's create a new variable which will be exactly this environment. And to get it, well, we first call our library Qlearning, from which we're going to call a function called make, in which we're going to input exactly the name of that environment. So it's not exactly called Lunar Lander, it is called exactly Lunar Lander V2. That's exactly the name of the environment that you have to enter, by the way, in this make function that you can also see here. You see, you have all the documentation here that can help you if you want to practice, for example, implement this yourself before you watch the tutorial with me. All right, so let's go back to the implementation. Let's paste that inside, and there we go. Now we have our environment. The next step, we're gonna get some parameters that we'll need later on in the training, like for example the state shape, the state size, the number of actions, right? Remember when we build the architecture of our neural network, well, we see that it's going to be the arguments of the network class, right? The state size, the action size. So that's actually what we're gonna get right now while setting up this environment. So we're gonna start with the state shape, which is of course this vector of 8 inputs that we saw 2 tutorials ago when I explained to you the observation space and the action space. So here we go, state shape, and to get it, well, we're going to call our environment, the variable env, from which we're going to call this following attribute observation space, from which we're going to get the parameter shape. And that will give us exactly the state shape. And now we have the state shape, that's good, but we also need the state size. So I'm creating a new variable which I'm going to call state size, and which will be exactly, well, the number of elements in this input state, meaning the 8 parameters describing at each time step the state of the environment. Remember the coordinates of the lander, then the coordinates of the velocity vector, etc. Right? We saw that together 2 tutorials ago, and it's also, of course, in this Lunar Lander Gymnasium documentation. So state size, to get it, well, let's be efficient. Let's take this, because actually the state size is going to be the first index of this env observation space.shape. And so the first index is going to be 0, because indexes in Python start from 0. All right. So we're going to do some prints at the end to see that we have the right parameters. Then after the state size, well, naturally we're going to get the number of actions. So let's call this number actions. And then how we're going to get that? Well, it's not going to be with observation space, but of course with another attribute called action space. So we're going to take our environment again, env, from which we're going to call this time the action space. Here it is, action space. And then we just need to add a dot and n to get exactly that number of actions. All right, we'll do another print later on to show the number of actions, which is of course 4. Remember, do nothing, move left, move right, or keep the same direction while slowing down the descent. And so here we go. That's the parameters I wanted to get for now, which we will use later. And now let's do some final prints to make sure we have the right parameter values. So let's start with the state shape, which I'm first going to enter in quote, state shape. Let's see exactly what it is. And so here I'm separating the string with a comma. And then after the comma, I put the value of state shape, which is of course given by our variable state shape, which we just created. All right, this one, yes. Now let's copy this to do the 2 other prints. First for the state size, which is of course given by our variable state, well, size. And then finally, let's print the number of actions. So here I'm going to replace that string by number of actions. And of course here, the variable is going to be number actions. All right, we should be good. Let's run this cell to see what happens. We should get 3 prints. Well, before we run the cell, let's actually expect what we're going to get. For this, the state shape, well, we're expecting a vector of 8 elements. Therefore, it's going to be 8, nothing in parentheses. Then the state size, we understood that it is 8, right? The position coordinates, the velocity coordinates, 8 in total. And then the number of actions, well, we perfectly understood that it is 4, all right? So that's what we expect. Now let's run this to see if we're right. And there we go. State shape, a vector of 8 elements. State size 8. 8 input values in each state of the environment at each time step. And then number of actions 4. Perfect. So we're good to go for the next step of this training implementation, initializing the hyperparameters. I look forward to seeing you in that next tutorial. And until then, enjoy AI. Hello my friends and welcome to the second step of the training implementation, initializing the hyperparameters. So now what we're about to do is simply to create some new variables while at the same time initializing them with a certain value. Alright, so I'll show you. Let's create a new code cell. The first variable we're going to create and initialize is the learning rate. Alright, so that's the name I choose for the variable. And then we're going to initialize its value to 5 times 10 at the power of minus 4. Alright, 0.0005. Okay, now the question is, why do we choose such a value for the learning rate? Well, again, that's after a lot of experimentation, trial and error, to get the best performance at the end when training the AI to land on the moon. Okay, so no rule of thumbs again. This is the best value after experimentation. Next, the next variable is going to be mini batch size, which refers, of course, to the number of observations used in one step of the training to update the model parameters. And so now, is there an optimal value? Well, not really this time. The usual value we choose based on common practice is actually 100. That's a good size of mini batch for deep Qlearning. All right? Then, next hyperparameter, the discount factor, also called gamma. So I'm going to call it discount factor just for educational purposes, just to make it super clear for everyone. But if you're used to gamma, you can of course call it gamma. And what are we going to initialize it to? Well, first, let's remind that the discount factor represents the present value of future rewards. So, for example, if we have a low discount factor close to 0, well, that will make the agent short-sighted by only considering the current rewards. However, if we have a discount factor close to 1, well, that will make the agent consider the future rewards in its accumulation of the total reward. And actually, we will get the best performance with a good consideration of the future rewards as opposed to being short-sighted. And therefore, we're going to choose our discount factor gamma to be 0.99. All right, close to 1. Then next parameter, well, that's going to have to do with our next step here, implementing experience replay. I'm talking, of course, about the replay buffer size. And what is that? Remember, that's the size, basically, of the memory of the AI, meaning how many experiences, including the state, the action, reward, next state, and whether done or not, in the memory of the agent. You know, the training to sample and break the correlations in the observation sequences. All right, and I remind that the purpose of that is to stabilize and improve the training process. And so now, what is a good replay buffer size? Well, we're going to choose to store 100,000 experiences in the memory. Let's actually note it like that. Int of 10 at the power of 5. All right, 100,000 experiences stored in the memory of the AI, which will stabilize and improve the training process. Perfect. And now we have one final parameter, which is the interpolation parameter used for the training. So that's the parameter that will be used in the sub-update of the target networks. A very important parameter, also called tau, but again, for the purpose of this training, I'm going to call it interpolation parameter. All right. But of course, if you're used to tau, you can call it tau. Great, so what is a good value of this parameter? Well, again, after experimentation, after testing several values of this hyperparameter, I can tell you already that the best value, the optimal value to train our AI to land on the moon is actually 0.001, right? Which we can know this way, 10 at the power of minus 3. Alright, and that's it. That's it for the initialization of the hyperparameters. We're now ready to move on to the next step, implementing experience replay. I can't wait to do that with you in the next tutorial, but please make sure to get some energy for it because we'll have 3 methods to implement inside the replay memory class. Alright, so now let's execute this cell and I'll see you in the next tutorial for this next step. And until then, enjoy AI. Hello my friends and welcome to this new step of the training implementation, implementing experience replay. So here we go, let's create a new code cell. We have a lot to do in this cell and we're going to start by creating a new class, which we're going to call replay memory class. That's the usual name we give to the class that basically implements experience replay. And then in parentheses, we're going to specify object, meaning that there's no inheritance this time that we're using, object, and then colon, and here we go. Let's start with the constructor method to initialize the replay memory object. All right, so that's of course the init method, which will take self, to refer to the object, and then another argument which will be capacity, the capacity of the memory. And here we go. So first, we're going to implement a line of code that will be useful if you want to execute this code outside of Colab, for example, on a Jupyter notebook with your machine, if you want to use a GPU. So we're just going to implement this self.device equals, then we call the torch library, from which we're going to call the device function. And then in parentheses, we're going to specify in quotes, CUDA colon 0, meaning we're going to use the GPU if torch.cuda.is underscore available, there we go, is equal to true. Basically, that means that if CUDA by torch is available, then we're going to use the GPU. And then else, we're going to use the CPU. Okay? So that's just useful for if you want to execute this code and make the training faster and more performant using a GPU. All right? Then we're going to take care of the capacity here. So we're going to call our object again self, from which we're going to create the capacity object variable, which we're going to initialize to the capacity argument here, which will be specified later on when we create an instance of the replay memory class. Okay, so we'll see what it is exactly later, but for now, that's how we're going to initialize the capacity variable of our object. All right, so here we go, capacity, which by the way is the maximum size of the memory buffer. Perfect. Then we're going to create a new object variable, which will be self.memory, which is of course the list that will store the experiences, each one containing the state, the action, the reward, the next state, and whether we are done or not. And we're going to initialize that to an empty list, all right, in square brackets. Okay, and that's it for the init method, the constructor method that initializes the replay memory object. And so now we're going to move on to the next method, which will be the push method that will add an experience event into the memory buffer. So let's take a little break here. We'll do that in the next tutorial. And until then, enjoy AI. Hello my friends and welcome to this new tutorial. In this one, we're going to implement a new method of the replay memory class, which will add an experience into the memory buffer. I remind that we chose our replay buffer size to have 100,000 experiences inside, and well, the method we're about to implement right now is the method that will add those experiences into this replay memory buffer while also checking that we don't exceed the capacity. Okay, so let's do this. Let's start by defining the method, which we're going to call push, and then in parentheses, we're going to enter two arguments. The first one is self for the object, and the second one is going to be the experience or event, as you want. That's the same thing. It's what basically contains, the state, the action, the next state, the reward, and that boolean done saying whether we are done or not. All right. So push self event and then colon, and then here we go. Let's implement that method. So first, remember that self.memory is initialized as an empty list. So the first thing we're going to do naturally is to append an event into that memory. And so very simply here, we take our memory object variable that was defined in the constructor init method. There we go, memory, and then we add a dot, and then the append function that you all know, which is a function that can append, meaning add an element into a list. And what do we want to add into this memory list? Well, that's of course the event, right? State, action, reward, next state, and done. Okay, so that's the first step. But now we must make sure that the memory buffer does not exceed its capacity, after we appended that event. And so just below, we're going to add an if condition saying, if the length of our memory, the memory of the object, if this length is larger than the capacity, which is self.capacity, then what are we going to do? Well, according to you, which event should we remove from the memory? Should it be the most recent event or the oldest event? Well, it should rather be the oldest event, right? Because the oldest event is at this point less relevant than the newest event. Okay, so let's delete that oldest event. And to do so, we're going to delete what we want to delete, which is exactly, well, the first element of our memory, meaning the memory of the object. And how do we get that first element? Well, of course, we specify in square brackets the index of that first element, which is, of course, the index 0. All right, and that's it. That's all we need to do in order to implement this push method that adds successfully an experience event into the memory buffer while making sure that the memory buffer does not exceed its capacity by removing the oldest experience if necessary. Okay, so now we're good to go for this second method. So now we're going to implement the third one, which is going to be the sample method that will randomly select a batch of experiences from the memory buffer. So if you want, practice yourself implementing this before we do the tutorial together. And well, whenever you're ready, I look forward to seeing you in that next tutorial to implement this. And until then, enjoy AI. Hello my friends, welcome to this new tutorial, and here we go implementing the last method of this replay memory class, which will be the sample method. Well, we choose to call it sample, which will randomly select a batch of experiences from the memory buffer. Alright, so here we go. Let's define this new method called sample, which will take as input, well, first self for the object, and then batch size, which will be the number of experiences that are going to be sampled in the batch. Okay, so then colon, and then here we go. So first we're going to create a new local variable which we're going to call experiences, and which will contain the experiences sampled in the batch. Alright, and so how are we going to get them? Well, we're going to use the random library from which we're going to call the sample function, which takes as input what, according to you? Well, of course, where do we want to sample the experiences from? Well, that's of course from the memory, self.memory, the memory of our object. Okay, then the second argument, what is it going to be? Well, it's going to be the number of experiences we want to have in this batch, and that's of course the batch size. I'm adding k here because that's this expected argument that we see here of the sample function, and that's the batch size. All right, perfect. So first step done, and now we're going to extract one by one the different elements of each sampled experience, meaning that, remember, an experience contains the state, the action, the reward, the next state, and the boolean done. And so we're going to extract and stack those elements one by one. All right, so let's start with the first element of an experience, which are the states. And so how are we going to do this? Well, first, we're going to call numpy, from which we're going to call the vstack function that will stack the states and the sampled experiences together, right, by extracting them and then stacking them. And so since it's a function, I'm adding here parentheses, and then I'm going to do a one row for loop. You know this, right? That's like a for loop within a list. So you add a pair of square brackets here, and then I'm going to do this for e in experiences. We're going to stack the first elements in those experiences, and therefore that's of course e of index 0, right? The states have the index 0 in each experience because it's the first element of the experience composed of state, action, reward, next state, and done. Okay, so we're getting all the states for all the experiences that were sampled. However, we must just check that each experience in this for loop is existent. And the way we're going to check this is just with an extra if condition saying if e, the experience, is not none. Alright, and that's it. So at this point we have just stacked all the states together from the sampled experiences. Good, but that's not enough. Now what we also need to do is convert these stack of states into PyTorch tensors, because then, you know, we're going to work with PyTorch to do the training and especially the neural network when updating the model parameters through backpropagation, and therefore we need to convert these states here into PyTorch tensors. And so how are we going to do this? Well, we're going to do this with another function from the torch library. So I'm calling the torch library first, and then this function is very simply from underscore numpy. And that's exactly what will convert these numpy arrays, because now this is a numpy array. And so I'm closing the parentheses here. There we go. And so now with this torch.fromNumpy, well, this numpy array becomes a torch tensor, a PyTorch tensor. Okay, then almost done, but we also need to make sure that the data type of these states, now PyTorch tensors, is only float. And that's again in order to give a certain format expected then by the torch functions and classes that will perform the training. And so to make sure of that, we're just going to add a dot float and then just some parentheses. That will make sure the data type is set as float here. And then remember, because we have our device, whether we are using a CPU or a GPU, we're just going to add at the end dot to self.device, one of the variables of our object, and that's just in order to move this stack of states into the designated computing device, whether it is a CPU or a GPU. Alright? And that's it. That's how we stack the states together by making sure they're torch tensors, the data type set as float, and moved to the designated computing device. Perfect. So now we're going to sample the next elements in the experience, meaning next the action. So what I'm going to do is I'm going to copy this line of code, then paste it right below, and then simply replace the states here by the actions, and of course the index here 0 by 1, because the action is the second element in the experience, therefore the element of index 1. And then, however, is or should it be set as a float? Well, no, because remember the actions can either be 0, 1, 2, or 3. There are 4 actions, and therefore it's better to set the data type here as a long integer. Alright? So then we're good to go. Then next sample of elements, well, that's going to be the rewards, of course. That's the third element in the experience. So I'm replacing here again states by rewards, and then of course the index 0 by 2. The third element in the experience, therefore the element of index 2. And then for the type, is it going to be a float or a long integer? Well, that's going to be a float, of course. So all good here. Then next sample of elements, well, these are going to be the next state. So here I'm going to replace states by next states, and then the index 0 by 3. All right, the fourth element in the experience, therefore the element of index 3. And then, is it going to be a float? Yes, because you know we have angles, we have velocity values, coordinates, so it's definitely a float rather than a long integer. It's just like the states, basically. Okay, and then, finally, let's take care of the last elements in the experiences, meaning the dones. So first I'm going to replace the states here by dones, then the index here by, of course, 4, the last element in the experience, therefore the element of index 4. And then, however, here there's a little difficulty. For the type, it's not going to be directly float. In fact, we have to set the data type first as the Boolean type, which is uint8. And the way we're going to do this is just in between those two parentheses here, we're going to add a dot asType, which is a function that sets a type, a data type. And it is inside this asType function that we're going to specify the uint8 Boolean data type, which we're going to call with numpy. Therefore, I'm adding np here, then dot, and then there we go, uint8. And this, the np.uint8 data type, is used to represent Boolean values before converting them into float tensors. Alright, and for the rest, we're good to go. So now we can just finish this sample method by, of course, returning those samples of elements, starting with the sample of states. Then here there's a little trap. Naturally we want to say the sample of actions, but actually from what is expecting then in the training, we actually have to return the sample of next state. You will see why exactly later. Then the sample of actions, and then the sample of rewards, and finally the sample of dones. There we go, and we're done with the sample method from the replay memory class. So double congrats, not only you implemented that sample method, but also you implemented fully that replay memory class. So now let's execute this cell to make sure we did everything right, and that seems to be the case. Perfect. Congrats again, that was a big class to implement. So now we're ready for the next step, implementing DQN class. It's going to be an exciting one. We're approaching very soon that exciting training. I can't wait to show you this and show you the final result. And until then, enjoy AI.